Hi guys, my name's Tristan, and I'm going to talk to you about power and absorption of electromagnetic waves. So I thought we'd start by a couple diagrams. So the top diagram shows electric and magnetic waves in free space. So as we can see, there's no attenuation of the waves. They stay constant as they propagate through Z. And the same with H, it stays constant. Whereas in a conducting media, shown in the graph below, we can see that there is attenuation in the electric wave, and there's attenuation in the magnetic wave as well as they move through Z. And we will quantify this later in the video. So now we're going to start off by defining power for electromagnetic fields, and we can see that the electric field has units of volts per meter, and the magnetic field has units of amps per meter. And we know that because power is voltage times current, it has units of volts times amps, which is units of watts. So we will use this concept to derive a power equation. So first, we're going to start off with Maxwell's equations, specifically Faraday's law, which states that the curl of E is equal to the negative time rate of change of B, and Ampere's law, which states that the curl of H is equal to the time rate of change of D plus J. And we're going to assume, for this video, we're going to assume simple media. So we're going to assume B is equal to mu H, D is equal to epsilon E, and J is equal to sigma E. So we're going to start off by taking the divergent, or we're going to dot this with H, that equation, and we're going to dot Ampere's law with E. So solving this, we get the curl of E dotted with H is equal to negative time rate of change of H. We're going to sub in our simple media, and we're going to do the same to the other side. Dotted with E is equal to the time rate of change of D plus J. Actually, we're going to sub in our simple media. So we're going to have epsilon rho E dotted with E plus sigma E squared, and the magnitude. So now what we're going to do is we're going to take these two equations and we're going to subtract them. And then we're going to equate the two sides. So on the left side, we're going to have curl of E dotted with H minus the curl of H dotted with E is equal to, and we're going to pull a minus out in front, and we're going to have minus mu H dotted with H plus epsilon times root of E dotted with E plus sigma E squared. And we can see on the left side here that this is an identity, and we can see that this side will be equal to the divergence of E cross H. So subbing this in, we can see the divergence of E cross H is equal to the left side again, mu rho H squared by T plus epsilon Alright, and now look at the left side. We can kind of see something similar to the divergence theorem. So what we're going to do is we're going to apply the divergence theorem. So we're going to take the volume integral of this entire equation, which allows us to write the right side as a surface integral of E cross H and we can then write the left side as a minus integral. We're going to pull the time derivative out in front, and we're going to get a mu h squared over 2 plus epsilon e squared over 2 plus sigma e squared. And this will be all in the integral. So now we can see that on the left side, we have E cross H over a surface. And we know that because E has units of volts per meter and H has units of amps per meter, that this term will have units of watts per meter squared. But because we're taking a surface integral, the meters squared will be cancelled, and the left side will just be equal to power. So we can clearly see that the left side is equal to power. So what we are going to do to make notation better is we're going to define a pointing vector. And Pointing was the man who did this whole transformation. So the pointing vector is defined as S is equal to E cross H. And this is very useful as it allows us to define a vector that we can actually quantify, as we can measure power, but we can't actually measure an electric or magnetic field. So now we have the surface integral of the pointing vector is equal to the negative volume integral of this side. So here we can see we have power. And on the right side, we can see this sigma term. This is going to be ohmic loss due to the conducting media. And then the other term on the right side, this is going to be, this has units. If you look at it, it has, because you have volts squared, amp squared, this is going to have units of joules per meter cubed, or energy density. So this term is equal to the energy density of the fields. And because we're taking the time derivative, it'll be then equal to power. Take the volume integral, it'll be equal to watts as well. So another way to define this, where we don't have to worry about time, is the time average power. And we do this using phasor notation. So phasor notation for E is equal to E naught e to the j omega t, and phasor notation for H is equal to H naught e to the j omega t. So we define the time average power as the pointing vector time average is equal to 1/2 the real part of E phasor cross H phasor conjugate. And this H phasor conjugate allows us to write H phasor as H naught e to the minus j omega t, which cancels out the omega t terms inside the real part and allows us to write it just in terms of space, not in terms of time. So we can now write E naught e to the j omega t cross H naught e to the minus j omega t. The omega t's cancel, and we get 1/2 the real part of E naught cross with H naught. And SF. So this is our time average power, which allows us to measure the amount of power transmitted over an area without having to worry about time. All right, so now that we have an understanding of how power is defined, I'm just going to actually quickly go back. If you look at this S vector, it is defined as E cross H. So if we go back to these graphs, we can see that E cross H, the pointing vector, is actually going to point in the direction of propagation. So the pointing vector is orthogonal to the E and H fields and points in the direction of propagation. So now let's talk about absorption. So absorption is due to material properties, mostly due to the amount of conduction a material can, or how current conducts in a material. So to start off, we're going to look at phasor notation of Maxwell's equations. So we're going to write the same two equations as we had before. So we're going to have Faraday's law written in phasor notation and assuming simple media. And we're going to have Ampere's law, also assuming simple media. So we're going to have sigma plus j omega epsilon. And we're going to pull the E field out of both of these terms to allow us to see that this term acts as more of a complex permittivity. So now, in order to truly see this term, we're going to try and derive a wave equation. So we're going to use Faraday's law on the left, and we're going to take the curl of that. So we're going to take the curl of E is equal to minus j omega h, or mu curl of h. And we can see on the left side that we have an identity here. So this can be equal to the gradient of the divergence of E minus the gradient squared of E, or the Laplacian. And we know that in a conducting media, because of the conducting media, we know that the divergence of D is equal to 0 because there's no surface charge on the conductor. So we can say that the divergence of E is equal to 0. So now rewriting this once again, we can say that we have del squared E is equal to, and what we're going to do is we're going to take this term here and we're going to sub it into this equation. So the divergence of E squared is equal to j omega mu sigma plus j omega epsilon E. And moving the right side over to the left side, you can say that the Laplacian of E minus j omega mu sigma plus j omega epsilon E is equal to 0. And we can see here that this is a wave equation, which is very useful. So now that we have a wave equation, we can start to look at solutions for the wave equation. But we want to get into a term that is more useful to us. So what we're going to do is we're going to define a vector, or a constant, gamma. And we're going to say gamma squared is equal to j omega mu sigma plus j omega epsilon. And just to expand it, this is equal to minus omega epsilon plus j omega mu sigma. And what we can see here is that we're going to have two terms in this gamma. We're going to have this term, which is equal to a conduction current. We're going to have this term, which is equal to a displacement current. So now that we have our wave equation in a form that's better, we're going to rewrite it. Minus gamma squared E is equal to 0. And the generic solution to these wave equations is E is equal to E naught plus a constant e to the minus gamma z And we're going to assume it's in the x-hat direction as we defined in our graphs above. So now looking at gamma further, we can also define gamma as equal to alpha plus j beta. And over on the left, we have gamma squared. So in order to solve for alpha and beta, we square the right side. And we end up getting alpha is equal to omega root of mu epsilon over 2, another root 1 plus sigma over omega epsilon squared minus 1. And we're going to get beta is equal to something very similar. We're going to get mu epsilon over 2 root 1 plus sigma over squared plus 1. And that's the difference. In alpha, we have this minus, and in beta, we have this plus. So we can see that when sigma is equal to 0, alpha is equal to 0, but beta is not equal to 0 due to this minus and plus difference in this term. Because in both these cases, this term would go to 0, this term would go to 0. So therefore, alpha is defined as the attenuation constant, and beta is defined as the phase constant. And back to this solution to the wave equation over here, kind of as an aside. So the solution to the wave equation, we just wrote the forward wave. Generally, there would be a backward wave term shown as plus e naught minus e to the omega z in the x-hat direction. But in this application, we're going to look at a one-way source. So we're going to just ignore this term. We're going to say this term is equal to 0. So what we really want now that we have a phasor E is we want to convert this back to the instantaneous domain so that we can plot it. So what we're going to do is we're going to convert it back to instantaneous form. So we're going to have an E is equal E in terms of Z and T is equal to the real part of our E phasor, E to the J omega T in the x-hat direction. And just expanding our E phasor, what I'm going to do here is I'm also going to expand gamma is equal to alpha plus j beta. So we're going to have E naught plus e to the minus alpha z, e to the minus j beta z, e to the j omega t in the x-hat direction. And solving this, we're going to have an e naught plus e to the minus alpha z cosine omega t minus beta z in the x-hat direction. So now we can see that in a conducting media, we are going to have an attenuation which is an exponential decay. And this exponential decay is shown in this graph as an exponential decay here. This is equal to e to the minus alpha z. So as you move through space, you attenuate the wave further due to this attenuation constant. And we can do the same for H. So in simple media, free space. In free space, we know that E naught plus is equal to, or H naught plus is equal to E naught plus over eta naught, where eta naught is in terms of the permittivity and the permeability of free space. But because we now have a conduction term as well, we define H naught plus is equal to E naught plus over a complex eta. And this complex eta can now be written as a magnitude of eta and a phase shift. So eta will now it'll scale our H field while also adding a phase shift. So now we can write the instantaneous form of the magnetic field. Similarly, we can write it as the real part of E naught plus over the magnitude of eta e to the minus alpha z, e to the minus j beta z, e to the j omega t, and now we're going to have an e to the minus j theta n as well in the y direction. And the y direction is due to the right-hand rule. If e is pointing in x, then e cross h must point in z, so h must be in the y direction. So now our magnetic field solution is equal to E naught plus over the magnitude of eta, e to the minus alpha z, the same attenuation constant, cosine of omega t minus beta z minus theta n in the y hat direction. So those are our two solutions. We have our E field here, and we have our H field here. And as we can see, the H field also attenuates, and there is a phase shift theta n here as well. Thank you for watching. I hope this helped, and see you next time.